How trees communicate through underground networks. Hello and welcome back to Sleepy Science Facts. Tonight, we're going to take a gentle journey beneath the forest floor, into a hidden world that connects every tree, every plant, every living thing in ways that would have seemed like pure fantasy just a few decades ago. So settle into your pillows, let your breathing slow, and prepare to discover the secret language of trees. Close your eyes for a moment and imagine a forest. Perhaps you see towering redwoods, or a peaceful grove of birches, or maybe the twisted oaks of an ancient woodland. Whatever forest comes to mind, I want you to imagine something else now. Beneath every tree you're picturing, stretching out in every direction, there exists an intricate network of connections, a kind of natural internet made not of fiber optic cables, but of living fungal threads finer than the finest silk. Now let us gently begin to descend into the forest floor, one fact at a time. Fact 1. The underground network that connects trees is called the mycorrhizal network, and the fungal threads that make it up, called hyphae, can be as thin as 2 to 5 micrometers in diameter. To put that in perspective, a human hair is about 50 to 70 micrometers thick, making these threads 10 to 35 times thinner than a single strand of your hair. These impossibly delicate filaments weave through the soil in numbers that challenge comprehension. In a single teaspoon of healthy forest soil, there can be several miles of these fungal threads, all connecting, communicating, transporting nutrients and information between trees. Fact 2. The term Wood Wide Web was coined by nature writer Richard Grant in 1997, but the scientific understanding of mycorrhizal networks really gained momentum through the work of forest ecologist Susan Simard in the late 1990s. Her research at the University of British Columbia revealed that trees weren't the isolated individuals we'd always assumed them to be. Simard's early experiments involved growing Douglas fir and paper birch trees together and using radioactive carbon isotopes to trace the movement of sugars between them. What she discovered was revolutionary. Fact 3. In Simard's experiments, she found that the trees were sharing carbon through the underground fungal network. When she shaded the Douglas fir seedlings but left the birch in sunlight, the birch would send excess carbon to the fir through the network. When she reversed this by shading the birch instead, the fir returned the favor, sending carbon to the birch. This wasn't competition. This was cooperation, resource sharing on a scale and through a mechanism that nobody had predicted. The trees were taking care of each other. Fact 4. These mycorrhizal partnerships between fungi and plant roots are ancient, dating back approximately 400 million years. In fact, scientists believe that these fungal partnerships were essential for plants to colonize land in the first place, helping them extract water and nutrients from soil when their root systems were still primitive. For hundreds of millions of years, plants and fungi have been evolving together, refining their communication systems, developing ever more sophisticated ways to support one another. The forest you walk through today is the result of this extraordinarily long partnership. Fact 5. The fungi in these networks aren't doing this work out of pure altruism. The relationship is mutualistic, meaning both parties benefit. While the fungi help trees absorb water and nutrients, particularly phosphorus and nitrogen, from the soil, the trees provide the fungi with something equally precious: sugars created through photosynthesis. The fungi can't photosynthesize themselves, you see. They can't capture the sun's energy and turn it into food. So they've evolved to become the ultimate middlemen, trading their extraordinary ability to extract minerals from soil and decomposing matter for the tree's ability to capture light and transform it into energy. Fact 6. A single mycorrhizal fungus can connect multiple trees of different species, creating an interspecies communication network. A typical forest might contain dozens or even hundreds of tree species, all linked together through overlapping fungal networks, creating a kind of biological internet that spans the entire forest. Imagine if you could instantly share resources with your neighbor or with someone across town, simply by willing it through a network in the ground. That's essentially what trees do every single day. Fact 7. Mycorrhizal fungi increase a tree's effective root surface area by anywhere from 100 to 1,000 times. The finest roots a tree can produce are still relatively thick and clumsy compared to fungal hyphae, which can penetrate tiny pores in the soil and access resources that would otherwise be completely unreachable. It's like having millions of tiny assistants, each one capable of squeezing into spaces you could never reach yourself, each one bringing back nutrients and minerals to sustain you. Fact 8. There are two main types of mycorrhizal fungi, ectomycorrhizal and endomycorrhizal, also called arbuscular mycorrhizal. Ectomycorrhizal fungi form a sheath around tree roots and are most commonly associated with trees in temperate and boreal forests, like oaks, pines, and birches. Endomycorrhizal fungi actually penetrate the root cells themselves and are found in association with about 90% of all plant species, including most tropical trees. Each type has its own strategy, its own way of connecting with its plant partners, but both create those essential threads that link the forest together. Fact 9. Large, old trees act as hub trees or mother trees in the forest network. These central nodes have more mycorrhizal connections than younger trees and play a crucial role in maintaining the health of the forest by distributing resources to trees that need them, particularly young seedlings struggling to survive in the shade of the canopy. Susan Simard found that a single mother tree could be connected to hundreds of other trees, functioning almost like a nurturing parent, ensuring that the next generation had what it needed to survive. Fact 10. Mother trees recognize their own offspring and preferentially send them resources. In experiments, Simard discovered that mother trees colonized with kin seedlings, their own offspring, would reduce their own root competition and increase the density of mycorrhizal fungal networks connecting them to their young, sending the young trees extra carbon through the network. This suggests a form of family recognition in trees, a concept that would have seemed absurd to scientists just a generation ago. Trees know their children and take care of them. Fact 11. When a tree is attacked by insects, it can send warning signals through the mycorrhizal network to nearby trees. These chemical signals prompt the receiving trees to increase their production of defensive compounds, essentially allowing them to prepare for an attack that hasn't yet reached them. The forest, it turns out, has an early warning system built right into its roots. When danger threatens one tree, all connected trees receive the message and can mount their defenses before the threat arrives. Fact 12. The chemical compounds that trees produce in response to insect attacks are remarkably sophisticated. Different species produce different combinations of defensive chemicals called secondary metabolites. Some of these make the tree's leaves taste terrible to insects. Others can actually interfere with insect digestion or reproduction, and some even attract the predators that feed on the insects attacking the tree. It's chemical warfare, conducted in slow motion, informed by messages passing through the ground beneath. Fact 13. The speed at which signals travel through mycorrhizal networks is surprisingly fast. While trees themselves operate on what seems like geological time to us, signals can propagate through the fungal network at speeds of up to 1 centimeter per second, meaning a warning could spread through a small grove of trees in a matter of minutes to hours. In the life of a tree, which might span centuries, this is lightning-quick communication. Before we venture deeper into this hidden forest network, if you're enjoying this peaceful journey through science, and if these facts are helping you relax into sleep, consider clicking the subscribe button now and like the video so that you don't forget or sleep off without doing so. You may already be asleep by the end of the video. Sweet dreams as you do so. Fact 14. Not all relationships in the mycorrhizal network are positive. Some plants, particularly those in the orchid family, have evolved to become mycoheterotrophs. They take carbon from fungi without providing anything in return, essentially stealing from the network. These plants have lost their ability to photosynthesize and instead parasitize the mycorrhizal network, drawing energy that originally came from other trees. Even in this cooperative underground world, there are thieves and freeloaders. Fact 15. The largest known organism on Earth is actually a mycorrhizal fungus. In Oregon's Blue Mountains, there exists a honey mushroom fungus, Armillaria solidips, that covers approximately 2,384 acres and is estimated to be between 2,000 and 8,000 years old. The mushrooms you might see popping up from the ground are just the fruiting bodies. The real organism is the vast network of fungal threads spreading through the soil. This ancient being connects countless trees across an area larger than 1,600 football fields, a silent giant beneath our feet. Fact 16. Mycorrhizal networks help trees share not just nutrients and warnings, but also water. During drought conditions, trees with access to water can share it with neighbors that are struggling. Scientists have measured water movement through these networks and found that trees in wetter microsites essentially help keep trees in drier spots alive during difficult periods. In a forest connected by mycorrhizae, no tree needs to face drought alone, as long as any tree in the network has water to spare. Fact 17. The carbon trading that happens through mycorrhizal networks changes with the seasons. During autumn, when deciduous trees begin to lose their leaves and their photosynthetic capacity drops, evergreen trees in mixed forests increase their carbon contributions to the network, essentially supporting their deciduous neighbors through winter. In spring and summer, when deciduous trees are in full leaf, the flow often reverses. The forest breathes in and out through the seasons, with resources flowing first one direction, then another, maintaining balance throughout the year. Fact 18. Different fungal species create different types of networks with different characteristics. Some create dense local networks connecting trees that are close together, while others send out explorers, long-distance runner hyphae that can extend several meters through the soil, potentially connecting trees that are quite far apart. It's as if the forest has both local area networks for nearby communication and long-distance connections for broader information sharing. Fact 19. When trees are stressed, whether from drought, disease, or damage, they often increase their investment in mycorrhizal partnerships. They send more carbon below ground to their fungal partners, essentially buying more insurance by strengthening their connections to the network when times are tough. This makes perfect sense when you think about it. In difficult times, community support becomes more valuable, not less. Fact 20. The structure of mycorrhizal networks shows remarkable similarity to other complex networks found in nature, including neural networks in brains, social networks among humans, and even the structure of the internet itself. They show what network scientists call small world properties, where any tree can reach any other tree through a relatively small number of connections. Mathematical analysis of these forest networks reveals patterns of organization that emerge naturally when information and resources need to flow efficiently through a system. Fact 21. The fungal networks beneath a forest aren't static. They're constantly growing, dying back, and reorganizing themselves in response to changing conditions. A hyphal thread might live for only a few weeks before being replaced, but the network as a whole can persist for centuries, constantly renewing itself like a river that's always flowing but never the same water twice. This dynamic quality means the forest's communication system is always adapting, always responding to new challenges and opportunities. Fact 22. Mycorrhizal fungi produce substances called glomalin, a protein that helps bind soil particles together into stable aggregates. It's estimated that glomalin makes up between 15 and 20% of the carbon stored in soils worldwide. This sticky protein, which can persist in soil for decades, essentially creates the structure that allows soil to hold water, resist erosion, and maintain the tiny air spaces that roots and organisms need. The fungi aren't just connecting trees, they're literally building the soil itself, grain by grain. Fact 23. In a single growing season, a vigorous mycorrhizal network can produce more than 8,000 kilometers of new fungal threads per cubic centimeter of soil. That's nearly 5,000 miles of new connections in a space smaller than a sugar cube, all of it happening in darkness, beneath our feet, while we walk through the forest above completely unaware. The scale of this hidden industry is almost impossible to comprehend. Fact 24. Trees can distinguish between different species of mycorrhizal fungi and show preferences for certain fungal partners. Research has shown that some tree species will allocate more carbon to fungal partners that provide them with more nutrients, essentially rewarding the fungi that serve them best. This creates a kind of marketplace underground, where trees and fungi negotiate their exchanges. Even without brains or consciousness as we understand it, these organisms have evolved ways to evaluate partnership quality and adjust their investments accordingly. Fact 25. The chemical vocabulary that trees use to communicate through mycorrhizal networks is staggeringly complex. Scientists have identified hundreds of different signaling compounds that can move through these networks, including amino acids, sugars, hormones, enzymes, and various secondary metabolites. Each compound potentially carries different information or triggers different responses. It's a language written in molecules, a biochemical conversation we're only beginning to learn how to translate. Fact 26. Some trees can reduce the growth of competitors through the network. Black walnut trees, for example, produce a chemical called juglone that's toxic to many other plant species. This compound can spread through soil and through mycorrhizal connections, suppressing the growth of nearby plants and reducing competition. It's a form of chemical warfare conducted through the very network that also enables cooperation. The underground web carries messages of both peace and conflict. Fact 27. Mycorrhizal networks can help trees survive clear-cutting and regrow forests more quickly. When a forest is cut down, if the mycorrhizal network remains intact, newly planted or naturally seeded trees can tap into this existing infrastructure immediately. They inherit not just nutrients, but connections, plugging into a network that might be centuries old. This is one reason why protecting soil integrity during logging operations can dramatically improve reforestation success. Fact 28. Different tree species host different communities of mycorrhizal fungi, but there's significant overlap. A single tree might form partnerships with dozens of fungal species, while a single fungal species might connect with multiple tree species. This overlap creates redundancy in the system. If one type of fungus dies back, others can take over its role, maintaining the network's function. Like any robust communication system, the forest network has backup systems built into its very structure. Fact 29. The depth at which mycorrhizal networks operate varies greatly depending on the forest type and soil conditions. In some forests, the most active zone is in the top few inches of soil where organic matter is decomposing. In others, particularly in drier climates, the networks can extend several feet deep, following tree roots down to more reliable water sources. The network adapts its architecture to the needs and opportunities of its environment. Fact 30. When scientists use radioactive tracers to track the movement of nutrients through mycorrhizal networks, they've discovered that resources don't just flow from strong trees to weak ones. Sometimes stressed trees receive more support, but at other times, resources flow toward the strongest, most vigorous trees. The network seems to make complex decisions about where resources are most needed or will be most useful. These patterns suggest optimization strategies that we don't yet fully understand. Fact 31. Mycorrhizal networks can extend the effective lifespan of a tree even after it's been cut down. Scientists have found tree stumps that remain alive for decades after the tree was felled, kept alive by carbon flowing to them through the network from nearby living trees. The stump continues to grow new wood, powered entirely by the generosity of its neighbors. In a very real sense, trees can refuse to let their companions die, sustaining them through pure connection. Fact 32. The presence of mycorrhizal networks affects how forests respond to climate change. Trees connected to robust networks show greater resilience to temperature stress, drought, and other climate-related challenges than isolated trees. The network allows forests to buffer individual trees against environmental extremes, spreading risk across the entire community. As our climate becomes more unpredictable, these underground insurance policies become more valuable than ever. Fact 33. Young tree seedlings that establish connections to the mycorrhizal network grow significantly faster than seedlings that remain unconnected. Research shows that connected seedlings can grow 2 to 5 times faster than their disconnected counterparts, particularly in the shaded understory where photosynthesis is limited. The network essentially subsidizes the growth of the next generation. A seedling born into a connected forest has won a kind of lottery. It inherits centuries of accumulated infrastructure. Fact 34. The fungal partners in these networks have their own means of obtaining nutrients beyond what they receive from trees. Many mycorrhizal fungi can break down complex organic molecules in soil, accessing nitrogen and phosphorus locked up in dead plant material, animal remains, and other organic debris. Some can even extract nutrients directly from rock, slowly weathering minerals through the secretion of organic acids. The fungi are biochemical engineers, unlocking resources that would otherwise be unavailable to the forest ecosystem. Fact 35. Temperature affects the activity of mycorrhizal networks. These networks are most active during warm, moist conditions when both trees and fungi are growing vigorously. During winter in temperate forests, network activity slows dramatically but doesn't stop entirely. Even under snow in the cold darkness, the threads maintain their connections, waiting for spring. The network has its own circadian rhythm, its own seasonal breathing. Fact 36. Not all tree species participate equally in mycorrhizal networks. Some species, called generalists, readily form connections with many types of fungi and through them with many other tree species. Others are more specialized, forming strong partnerships with specific fungal species. These differences affect how well different trees can integrate into the broader forest network. Like humans, some trees are natural networkers, while others are more selective about their connections. Fact 37. The discovery of mycorrhizal networks has changed forestry practices in some regions. Forest managers now recognize that preserving the underground network during harvesting operations can significantly improve the success of replanting efforts. Some silviculture practices now include leave trees, leaving scattered mature trees, standing specifically to maintain the mycorrhizal network for the next generation. We're learning that caring for forests means caring not just for what we see above ground, but for the invisible infrastructure below. Fact 38. Mycorrhizal networks can transport more than just nutrients and chemical signals. They can also transport electrical signals. Plants generate electrical potentials across their membranes, and these electrical signals can propagate through the network, potentially carrying information even faster than chemical signals. Some researchers believe this electrical component of forest communication might be more important than we currently realize. The forest doesn't just have a chemical internet, it might have an electrical one too. Fact 39. The density and complexity of mycorrhizal networks vary with forest age. Young planted forests often have sparse, poorly developed networks, which is one reason plantation trees are often more vulnerable to stress than trees in old-growth forests. As forests mature over decades and centuries, their underground networks become richer, more redundant, and more effective at supporting the forest community. An old forest is wise not just in the age of its trees, but in the sophistication of its underground connections. Fact 40. Some invasive plant species can exploit mycorrhizal networks to establish themselves in new environments. By tapping into the existing network, invasive plants can access the resources and infrastructure that native species took centuries to build. This is one mechanism by which certain invasive species can successfully compete with native vegetation. They're essentially hijacking the local communication system. The network's openness and generosity, normally a strength, can become a vulnerability when newcomers don't play by the established rules. Fact 41. Scientists studying mycorrhizal networks use sophisticated technology to map these underground connections. Ground-penetrating radar, DNA sequencing of soil samples, tracer isotopes, and even custom-built devices that can detect fungal threads all contribute to our growing understanding of forest network architecture. Each new mapping technique reveals layers of complexity we hadn't seen before. We're cartographers of an invisible landscape, slowly charting a world that exists just beneath the surface of the familiar. Fact 42. The relationship between specific tree species and fungal species has co-evolved over millions of years. Some partnerships are so ancient and so refined that neither partner can survive without the other anymore. The tree can't access enough nutrients without its fungal partners, and the fungus can't obtain enough carbon without its tree hosts. They've become obligate symbionts, locked in mutual dependence. This reminds us that independence is sometimes an illusion. We're all embedded in webs of mutual support, whether we acknowledge it or not. Fact 43. Mycorrhizal fungi can help trees cope with toxic substances in soil. In contaminated soils containing heavy metals like cadmium, lead, or mercury, mycorrhizal fungi can bind these toxins, preventing them from entering tree tissues. Some fungi can even break down certain organic pollutants, essentially helping to detoxify the soil while maintaining their partnerships with trees. The network isn't just about sharing resources. It's also about collective protection from environmental threats. Fact 44. The fruiting bodies we see above ground, mushrooms, puffballs, truffles, are just the reproductive structures of the vast fungal networks below. These brief appearances, often lasting only days or weeks, are the only visible signs of organisms that might span acres underground. It's estimated that only about 5% of a fungal organism's biomass is ever visible above ground at any one time. When you see a mushroom, you're seeing the tiny tip of something immense and mostly hidden. Fact 45. Research has shown that trees can alter their growth patterns based on signals received through mycorrhizal networks. If a tree receives signals indicating that resources are plentiful in the network, it might invest more energy in above-ground growth, trunk thickening, and branch extension. If signals suggest resources are scarce, it might instead invest more in root growth or in its contributions to the fungal network, essentially strengthening its connections during difficult times. Trees make strategic decisions about growth and investment, informed by information flowing through the network beneath them. Fact 46. The economics of the tree-fungus exchange are surprisingly sophisticated. Research has shown that trees don't just provide a constant supply of carbon to their fungal partners. They regulate how much they give based on how much they receive in return. If a fungal partner provides abundant nutrients, the tree rewards it with more carbon. If the fungus underperforms, the tree reduces its investment. This dynamic negotiation keeps the partnership balanced and mutually beneficial. Even without price tags or currency, markets exist beneath the forest floor. Fact 47. Some researchers believe that mycorrhizal networks might play a role in forest succession, the gradual change in forest composition over time. Pioneer species that colonize disturbed areas often form different mycorrhizal partnerships than the late successional species that eventually replace them. As the network changes, it might actually facilitate the transition from one forest type to another, like an invisible hand guiding the forest's development. The network doesn't just support the forest as it is, it might help shape what the forest is becoming. Fact 48. Mycorrhizal networks are affected by human activities in complex ways. Nitrogen deposition from air pollution can disrupt these networks by making nitrogen so abundant that trees reduce their investment in fungal partnerships. Similarly, soil compaction from heavy machinery, changes in soil pH, and pesticide use can all damage mycorrhizal networks, sometimes with effects that last for decades. Our footprint on the landscape extends into realms we can't see, affecting relationships we're only beginning to understand. Fact 49. In tropical rainforests, where nutrients cycle rapidly and most are tied up in living biomass rather than soil, mycorrhizal networks are even more critical than in temperate forests. The moment a leaf falls or an organism dies, fungal threads begin breaking it down and transporting its nutrients back into the network, making them available to trees before the nutrients can leach away in heavy tropical rains. In these exuberant ecosystems, the network is less like a safety net and more like a high-speed recycling system that operates in real time. Fact 50. Trees can simultaneously participate in multiple overlapping mycorrhizal networks. A single tree might be connected to its neighbors through several different fungal species, each creating its own network with its own characteristics. These multiple networks interweave and overlap, creating redundancy and resilience. If one network is disrupted, communication and resource transfer can continue through others. The underground web is not a single network, but a network of networks, layered and interconnected in ways that create remarkable stability. Fact 51. The color and appearance of mycorrhizal fungal threads vary dramatically depending on the species. Some are bright white, gleaming like silk threads when exposed to light. Others are yellow, orange, brown, or even black. Under a microscope, these threads reveal intricate structures, branching patterns, specialized cells for nutrient absorption, and tiny droplets of stored compounds that shimmer like jewels. There's an entire aesthetic universe in the soil, invisible to us as we walk above, beautiful in ways we rarely consider. Fact 52. Mycorrhizal networks can help forests recover from fire. After a wildfire, the network in the soil often survives even when all above-ground vegetation is consumed. Tree roots and fungal threads deeper in the soil may remain viable, and this surviving network can give burned forests a tremendous head start in recovery. Seeds germinating in burned soil can immediately tap into this ancient infrastructure. The forest's memory persists underground, waiting patiently for the chance to rebuild. Fact 53. Scientists have discovered that the chemical signals trees send through mycorrhizal networks can vary in complexity. Simple warnings about insect attacks might involve just one or two compounds, but more nuanced information about the specific type of threat, its severity, or even the direction from which it's coming might be encoded in complex combinations of dozens of different molecules released in specific sequences. The forest's language has grammar and syntax, patterns of meaning we're only beginning to decode. Fact 54. In mixed-age forests, older trees often support younger ones through resource transfers that last for years or even decades. A mother tree might provide enough carbon to keep her offspring alive through their vulnerable early years when they're shaded by the canopy and unable to photosynthesize efficiently. This extended parental care through mycorrhizal networks increases the survival rate of seedlings by as much as 400% in some forest types. Parental investment, it turns out, isn't unique to animals. It's woven into the very structure of the forest. Fact 55. The mycorrhizal networks in Arctic and alpine environments are particularly crucial for plant survival. In these harsh climates where the growing season might last only a few weeks, plants can't afford to spend energy building extensive root systems from scratch each year. Instead, They maintain their connections to perennial fungal networks that persist through the winter, allowing them to access nutrients the moment conditions become favorable. In the harshest environments, community support isn't optional. It's the only way to survive. Fact 56. Researchers have found that stress in one tree can trigger a cascade of responses throughout a connected forest network. When a tree experiences severe drought stress, its distress signals can prompt neighboring trees to begin their own water conservation measures, closing stomata, redirecting resources to root growth, increasing production of stress-protective compounds, even before those neighbors experience water shortage themselves. The forest operates as an early warning system, with each tree serving as both sentinel and beneficiary. Fact 57. The metabolic cost of maintaining mycorrhizal partnerships is substantial. A tree might allocate anywhere from 10 to 50% of the carbon it produces through photosynthesis to its fungal partners. This represents an enormous investment, but one that pays dividends in enhanced nutrient uptake, stress resistance, and integration into the forest community. Trees in nutrient-poor soils tend to invest more heavily in these partnerships than trees in rich soils. Even trees understand that the value of a connection depends on what that connection provides. Fact 58. Mycorrhizal networks can transport defensive compounds between trees. When one tree produces chemicals to defend against a pathogen or pest, some of these compounds can move through the fungal network to neighboring trees, essentially allowing trees to share their medicine. This phenomenon has been documented with compounds that protect against root rot fungi, bark beetles, and various other threats. The forest has a kind of collective immune system, with immunity shared through underground connections. Fact 59. The structure of mycorrhizal networks shows seasonal variation. During spring and early summer, when trees are growing rapidly and nutrients are in high demand, fungal networks tend to be most extensive and active. In late summer and fall, some fungal species reduce their exploration of new soil areas and focus instead on maintaining existing connections and producing reproductive structures, the mushrooms that appear in autumn forests. The network breathes with the seasons, expanding and contracting in rhythm with the forest's yearly cycle. Fact 60. Some tree species can suppress the mycorrhizal connections of their competitors while maintaining their own. Through the release of specific chemical compounds, these trees can selectively inhibit fungal growth around the roots of competing species while promoting fungal partnerships with their own roots. This allows them to enjoy the benefits of the network while limiting their competitors' access to shared resources. Even in a cooperative system, there are strategies for gaining advantage. Fact 61. The genetic diversity of fungal partners affects forest resilience. Forests with a diverse community of mycorrhizal fungi are better able to withstand environmental stresses than forests with low fungal diversity. Different fungal species excel under different conditions. Some are drought specialists, others excel in cold or heat. Some are particularly good at extracting specific nutrients. This diversity provides insurance against environmental uncertainty. Diversity in the network below mirrors the importance of diversity in the canopy above. Both are essential for long-term forest health. Fact 62. Mycorrhizal fungi can bridge significant distances underground. While most connections are local, linking trees within a few meters of each other, some fungal species produce specialized runner hyphae that can extend 20 meters or more through the soil. These long-distance connections can link trees that have no above-ground interaction whatsoever, creating relationships between trees that might seem isolated from one another. The forest is more connected than it appears, with invisible threads linking even distant individuals. Fact 63. Trees growing in isolation, without access to mycorrhizal networks, show measurable signs of stress even when provided with adequate water and nutrients. They grow more slowly, produce more stress hormones, and are more susceptible to disease than trees of the same species growing in connected forests. This suggests that the benefits of network membership go beyond simple resource acquisition. Perhaps being part of a community provides benefits that transcend material exchanges, something more fundamental to well-being. Fact 64. The pH level of soil significantly affects mycorrhizal network formation and function. Most mycorrhizal fungi prefer slightly acidic conditions, with optimal pH ranging from 4.5 to 6.5. In soils that are too acidic or too alkaline, fungal growth is inhibited, and network formation is impaired. This is one reason why acid rain, which can dramatically lower soil pH, has such detrimental effects on forest health. The invisible chemistry of soil determines what connections are possible. Fact 65. Some mycorrhizal networks show what scientists call scale-free properties, meaning they have a few highly connected hub nodes and many less connected nodes. This architecture is similar to that of social networks, the internet, and even neural networks in the brain. It's an efficient design for information flow, allowing signals to reach any part of the network through a small number of steps while making the network relatively resistant to random damage. Nature has independently discovered the same optimal network architecture that human engineers use in designing communication systems. Fact 66. Mycorrhizal fungi produce enzymes that can break down complex organic compounds, including some forms of plastic and petroleum products. Researchers are exploring the possibility of using mycorrhizal fungi for bioremediation, cleaning up contaminated soils. The same networks that support forest health might also be deployed to heal damaged landscapes. The threads that connect the forest might also help reconnect us with damaged lands, facilitating healing on a massive scale. Fact 67. The transfer of resources through mycorrhizal networks isn't always equal or fair. Studies have shown that some trees consistently receive more than they give, while others are net donors. Interestingly, the net donors aren't always the largest or healthiest trees. Sometimes intermediate-sized trees provide the most resources to the network, supporting both their smaller and larger neighbors. The economics of the forest network are complex and don't always follow the patterns we might expect. Fact 68. When a tree dies, it can continue to influence the forest through the mycorrhizal network for years afterward. As the tree's roots and stumps slowly decompose, the fungi associated with them break down this woody material and redistribute its nutrients throughout the network. The dead tree essentially feeds the forest through the same connections that sustained it in life. Death in the forest isn't an ending but a transformation, with the deceased returning their substance to the community through fungal intermediaries. Fact 69. Mycorrhizal networks can influence the chemical composition of streams and groundwater. By affecting how trees take up and release various compounds, these networks influence what ends up washing into aquatic ecosystems. In some cases, robust mycorrhizal networks can reduce nutrient pollution in streams by helping trees capture nutrients before they leach into waterways. The web beneath the forest floor connects not just tree to tree, but forest to stream, terrestrial to aquatic. Fact 70. Different life stages of trees show different patterns of network participation. Seedlings are typically net receivers, drawing resources from the network to fuel their growth. Young adult trees often become net contributors, supporting the next generation of seedlings. Mature trees may become major hubs in the network, and ancient, declining trees often return to being net receivers, sustained by the network in their final years just as they were in their first. The forest network supports its members from birth through death, adjusting its flows to meet changing needs across the lifespan. Fact 71. The discovery of mycorrhizal networks has philosophical implications for how we understand plant intelligence and communication. While trees don't have neurons or brains, the behavior of forest networks, sharing resources, warning of danger, recognizing kin, making complex allocation decisions, suggests forms of information processing and communication that challenge our definitions of these concepts. Perhaps intelligence and communication are not single phenomena, but spectrums of possibilities, expressed differently in different living systems. Fact 72. Mycorrhizal networks respond to light cycles even though they exist in complete darkness. The trees connected to these networks operate on circadian rhythms, increasing their photosynthesis and carbon allocation to roots during daylight hours. The fungi respond to this daily pulse of resources, showing corresponding rhythms in their own growth and metabolism. The network pulses with a daily rhythm, synchronized to the sun it never sees. Even in perpetual darkness, life organizes itself around the light. Fact 73. Climate change is altering mycorrhizal networks in ways scientists are only beginning to understand. Warmer temperatures, changing precipitation patterns, and altered seasons are affecting both trees and fungi, but not always in the same ways or at the same rates. Some fungal species are expanding their ranges while others are contracting. The networks of the future may look very different from those of today. The web that has connected forests for millions of years is being rewoven by forces operating on a global scale. Fact 74. In experiments where researchers have severed mycorrhizal connections between trees, the effects are immediate and measurable. Disconnected trees show increased stress hormones within hours, reduced growth rates within days, and increased susceptibility to disease within weeks. Reconnecting trees to networks leads to equally rapid improvements in these metrics. The value of connection is not metaphorical or abstract. It's measurable in the chemistry and physiology of every tree. Fact 75. Some mycorrhizal fungi form connections not just with trees but with understory plants, creating networks that integrate multiple layers of the forest. A single fungal network might connect tall canopy trees with mid-story shrubs and ground-layer herbs, facilitating resource transfers and communication across the entire vertical structure of the forest. The network doesn't just spread horizontally. It connects the forest from soil surface to canopy, integrating all layers into a single, three-dimensional web. Fact 76. Researchers have found that trees can adjust the chemistry of their root exudates, compounds they release into the soil, to attract beneficial fungal partners and repel harmful fungi. This chemical signaling allows trees to actively recruit the fungal partners they prefer, essentially interviewing candidates for partnership positions. Even without movement or visible behavior, trees exercise agency in choosing their connections. Fact 77. The thickness of fungal mantles around tree roots varies with soil fertility. In nutrient-poor soils, these mantles can be quite thick, sometimes making up 20 to 40% of the root tip's total diameter. In rich soils, the mantles are thinner. The tree invests more heavily in fungal partnerships when those partnerships provide greater benefit. Investment follows need, and the physical structure of the network reflects the intensity of the demand it serves. Fact 78. Mycorrhizal networks can help trees survive transplant shock. When trees are moved from one location to another, maintaining connections to mycorrhizal fungi dramatically improves survival rates. Some nurseries now inoculate seedlings with appropriate mycorrhizal fungi before selling them, essentially giving young trees a starter kit for building their own network connections. We're learning to work with these networks rather than against them, to be facilitators of connection rather than disruptors. Fact 79. The time it takes for a newly planted tree to integrate into an existing mycorrhizal network varies considerably. In optimal conditions with receptive fungal partners nearby, connection can occur within weeks. In less favorable circumstances, it might take years. During this integration period, the tree is vulnerable, lacking the support system that will eventually sustain it. New arrivals must prove themselves worthy of inclusion, and inclusion brings responsibilities as well as benefits. Fact 80. Some researchers have proposed that mycorrhizal networks could be deliberately managed to improve forest health and carbon storage. By promoting the development of robust networks, perhaps through selective retention of hub trees or inoculation with beneficial fungi, we might be able to enhance forests' ability to capture and store atmospheric carbon dioxide. Understanding these networks opens possibilities for partnership with forests in addressing global environmental challenges. Fact 81. The energy cost of producing and maintaining mycorrhizal connections fluctuates with environmental conditions. During periods of abundant moisture and nutrients, trees may reduce their carbon allocation to fungi, essentially scaling back their investment when resources are readily available. During stress periods, this allocation increases dramatically, sometimes doubling or tripling as trees essentially pay for enhanced support services. The forest network operates on a kind of dynamic pricing system, where the value of connection rises and falls with circumstances. Fact 82. Mycorrhizal fungi have evolved specialized structures called arbuscules, tiny, tree-like branches that penetrate plant root cells. These arbuscules increase the surface area for nutrient exchange by up to tenfold, creating an intimate interface where carbon flows from plant to fungus and minerals flow from fungus to plant. Each arbuscule lives for only a few days before being absorbed and replaced, making this exchange site a place of constant renewal. At the most fundamental level, the partnership is maintained through structures that live briefly, die, and are continuously regenerated, connections sustained through endless small acts of giving and receiving. Fact 83. Forest fires affect mycorrhizal networks differently depending on their intensity. Low-intensity fires that burn through understory but don't kill large trees may actually stimulate network growth by clearing competing vegetation and releasing nutrients from burned organic matter. High-intensity fires that kill trees severely damage networks but rarely destroy them entirely. Surviving fungal threads become anchors for forest recovery. Even destruction can sometimes strengthen what remains, pruning the network and redirecting its energy toward regeneration. Fact 84. The mycorrhizal networks of coastal forests show adaptations to salt spray and occasional inundation by seawater. The fungi in these networks have evolved tolerance to salt concentrations that would kill most other fungal species, and they help their tree partners cope with these challenging conditions by regulating salt uptake and helping maintain proper water balance in plant tissues. Every environment shapes its networks differently, and the connections beneath coastal forests are as distinctive as the twisted, wind-shaped trees above. Fact 85. Researchers studying mycorrhizal networks in permafrost regions have discovered that these networks remain partially active even at temperatures well below freezing. During the brief Arctic summer, they explode into activity, but they never completely shut down. Even at -20 degrees Celsius, some metabolic activity continues, maintaining the threads that will support explosive growth when warmth returns. Life persists in the cold and darkness, waiting with infinite patience for its season to return. Fact 86. The volatility of compounds trees release into the air, their scents, is influenced by their mycorrhizal partnerships. Trees with robust fungal connections often produce different aromatic profiles than stressed, poorly connected trees. Some researchers believe these scent differences might actually be detectable signals, allowing trees to assess the health and network status of their neighbors through airborne cues. The forest speaks in scents as well as in underground chemical exchanges, creating layers of communication we're only beginning to recognize. Fact 87. Mycorrhizal networks in urban forests face unique challenges. Soil compaction from foot traffic and construction, pollution from vehicles and industry, salt from winter road treatments, and the heat island effect all stress these networks. Yet even in cities, where conditions are far from ideal, mycorrhizal networks persist, connecting street trees and park trees in fragments of the vast webs that once covered the landscape. The networks remember what was, maintaining their ancient patterns even in profoundly altered landscapes. Fact 88. The nitrogen-fixing bacteria that live in nodules on the roots of certain trees and shrubs, like alders and black locusts, interact with mycorrhizal networks in fascinating ways. These nitrogen fixers can share the nitrogen they capture from the atmosphere not just with their host plants, but with other plants in the network. A nitrogen-fixing tree essentially fertilizes its neighbors through the underground web. Some members of the forest community have special gifts they can share, and the network ensures these gifts reach those who need them. Fact 89. Trees can distinguish between mechanical damage, like a branch breaking in wind, and damage caused by herbivores. When insects or other animals feed on leaves, trees respond by sending specific warning signals through mycorrhizal networks. But when damage is mechanical, different signals are sent, or sometimes no signal at all. The network doesn't waste bandwidth on false alarms. The forest's communication system has evolved to be discriminating, filtering information to avoid overwhelming the network with irrelevant data. Fact 90. Mycorrhizal networks show what ecologists call functional redundancy. Multiple species of fungi can perform similar roles in the network. This redundancy is crucial for resilience. If one fungal species is eliminated by disease, climate change, or other factors, other species can expand to fill its niche, maintaining network function even as community composition shifts. The web persists not because any single thread is indestructible, but because so many threads weave together that the loss of some can be absorbed without collapse. Fact 91. In experiments tracking resource flows through mycorrhizal networks over multiple years, researchers have discovered that the pattern of exchanges between any two trees isn't random but shows consistency. Tree pairs that engage in substantial resource sharing in one year tend to do so in subsequent years as well. The network appears to maintain memory of past exchanges, with established partnerships persisting over time. The forest develops relationships, not just connections, bonds that deepen with time and repeated interaction. Fact 92. The mycorrhizal networks beneath old-growth forests show a complexity that cannot be quickly recreated. While planted forests can develop functional networks within a few decades, the intricate architecture of old-growth networks, with their highly connected hub trees, their diversity of fungal species, and their finely tuned exchange patterns, may require centuries to fully develop. Some things cannot be rushed. Ancient wisdom, whether in human culture or forest ecology, accumulates only through the passage of generations. Fact 93. Mycorrhizal fungi produce antibiotics that protect their tree partners from pathogenic bacteria and fungi. These compounds, released into the rhizosphere, the zone of soil immediately surrounding roots, create a chemically defended space where tree roots can grow with reduced risk of infection. In essence, the fungal partners provide not just nutrition but also medical protection. The network is guardian as well as courier, defending its members even as it connects them. Fact 94. The total length of mycorrhizal fungal threads in a single hectare of healthy forest, that's an area about the size of 2 football fields, can exceed 10 billion kilometers. That's enough to wrap around Earth's equator 250,000 times, or to stretch from Earth to the Sun and back more than 30 times. All of this exists in the top meter or so of soil, invisible, supporting every tree in that hectare. The scale of what we cannot see dwarfs the scale of what we can, reminding us that visible grandeur often rests on invisible foundations. Fact 95. Trees connected to mycorrhizal networks show different patterns of gene expression than isolated trees, even when both are growing under identical conditions. Hundreds of genes related to stress response, nutrient metabolism, and growth regulation are expressed differently depending on network connectivity. The network doesn't just provide resources, it fundamentally alters how trees function at the molecular level. Connection changes us at our deepest levels, influencing not just what we have but what we become. Fact 96. In tropical forests, Where many trees depend on animal dispersal of their seeds, mycorrhizal networks play an unexpected role in determining where new trees can successfully establish. Seeds that land in areas with appropriate fungal partners have dramatically higher survival rates than those that don't, essentially creating invisible maps of suitable habitat that guide the forest's regeneration patterns. The network beneath determines the possibilities above, shaping the future forest before a single seed germinates. Fact 97. Mycorrhizal fungi can transfer mineral nutrients with remarkable selectivity. Different fungal species specialize in transporting different nutrients. Some are phosphorus specialists, others excel at nitrogen transport. Still others focus on micronutrients like iron, zinc, or copper. A tree connected to multiple fungal species essentially has access to specialists for each of its nutritional needs. The diversity of the network provides comprehensive support, with different partners contributing different expertise. Fact 98. The water-conducting properties of mycorrhizal networks become critical during drought. Fungal hyphae can access water in tiny soil pores that roots cannot reach, and they can transport this water to tree roots even when the soil between the fungus and the root is completely dry. The fungi essentially create pipelines through dry soil, maintaining water supply when surface conditions would suggest none is available. In the hardest times, the network provides what seems impossible, finding resources where none appear to exist. Fact 99. Researchers have discovered that the electric potential differences between trees connected by mycorrhizal networks change in coordinated patterns, suggesting that electrical signaling might be occurring through the network. These voltage fluctuations are subtle but measurable, and they correlate with resource transfer events and stress responses. The forest may have an electrical nervous system we've only just begun to detect. Beneath our feet, in the darkness of the soil, signals flow at the speed of electricity, carrying messages we're only now learning to sense. Fact 100. The resilience of mycorrhizal networks to disturbance varies with network architecture. Networks dominated by a few highly connected hub trees are vulnerable to the loss of those hubs. Remove the mother trees, and the network can fragment. Networks with more distributed connectivity, where connections are spread more evenly among many trees, are more resilient to the loss of any single individual. Forest management practices that recognize this distinction can help preserve network function even when some trees must be harvested. Structure determines fate, and understanding structure allows us to act with greater wisdom and less harm. Fact 101. Perhaps the most profound lesson of mycorrhizal networks is this. They reveal that trees are not individuals competing for survival, but members of communities cooperating for mutual benefit. The forest is not a collection of trees but a superorganism, connected beneath the ground in ways that make each tree's success dependent on the health of the whole. What happens to one tree matters to all trees. What strengthens the network strengthens every member. What fragments the network diminishes every connection. In discovering how trees communicate through underground networks, we've discovered something equally important about the nature of life itself. That connection is not optional or supplementary to survival, but fundamental to it. That giving and receiving are not opposites but two sides of the same essential exchange. That community is not what happens after individuals survive, but what makes survival possible in the first place. The forest has been trying to teach us this for millions of years. Perhaps now, finally, we're beginning to listen. And as you drift towards sleep tonight, you might imagine yourself as part of a network too, connected to the people around you, to the living world, to the earth beneath your feet. You might imagine invisible threads of support and communication linking you to countless others, near and far. You might rest in the knowledge that you're not isolated, not alone, but woven into a web of relationships as ancient and essential as the forest itself. The trees know this truth, they've known it all along, and now so do you. Sleep well, the network holds you, the forest remembers, And tomorrow, when you wake, the threads will still be there, connecting everything to everything else, invisible but real, silent but speaking, holding the world together in the darkness beneath our feet.